All right, so if you take a look, like I said, we are looking at parametric equations today. We're going to add in some applications where we're talking about projectile motion. That's where the whole physics side of things is going to come into play here a little bit. But if you take a look at the warm-up that I gave you, here's what you should have come up with for problem number 1. Okay, here's what the graph looks like as you're working your way through it. Here's the different points that you should have come up with. One quick thing again, as you graph it, if you remember what I told you yesterday, I want you to put arrows on the graph so you're representing which motion, the motion of whatever we're talking about. Okay, so we know which direction things are going in. We started at this point, -2, -1, and then we worked our way around the sideways parabola. Okay, so I want you to put those arrows on there so that you can actually see the motion that's going on. So when you're plugging in your values of t, you're getting your values of x and y from the parametric equations and go from there. Now, I didn't put the actual points in the second one, like I said, just because they're a little bit messy, and you're going to get decimals and stuff on those next ones, and then approximate that. But here's basically what you should have come up with, something like this. Here's what the graph should have ended up looking like. Okay? Like I said, I didn't put specific points on here just because they're messy and things along those lines. But once you find those values and you do plot the points, you should end up with basically what it turns out to be is a half of an ellipse, the top half of an ellipse. Okay. And the reason it's only the top half, anybody tell me why? Yeah, because we're only going from 0 to pi. We're not actually going all the way around the unit circle. So we're not graphing the entire thing, we're only graphing half of it. Okay? 0 to pi is half the unit circle, therefore we end up with half of an ellipse. Okay? So just to give you an idea what the graphs should look like. Okay? Now, in number 3 then, here's the idea. When we eliminate the parameter, remember it depends on what you're looking at, depending on the problem. If you're dealing like in number 3, which really, going back to the first problem, if you're dealing with an algebraic problem, remember yesterday we had said you solve for t and then substitute. You're trying to eliminate t. That's why we're solving for it and then doing the substitution. So we get t out of the equation. So in this case, multiple people ask, well, which one do I solve? And the very simple answer, whichever one's easier to solve for t. It doesn't really matter. You'll get the same answer in the end, but take the one that's easier to solve. So I'm going to take the second one because all you have to do is multiply both sides by 2 to get t by itself. So if we do that, that means t is equal to 2y. Okay? If I just double both sides. And now if that's what t equals, now I can substitute it into the first equation. Okay? So that means x equals the quantity 2y squared minus 2. Take t out, substitute in what t is equal to. Okay? That's why we needed to solve for t on the first part. And now we simplify. Now we just simplify it down. We have to just square the 2y, which means we end up with an equation of x equals 4y squared minus 2. There's your equation in this case in rectangular coordinates. And back to what you're used to, which, by the way, should connect up to the graph because since it's squared, it's a parabola. Since it's y squared, it opens sideways. Just like we talked about when we were dealing with conic sections. Y squared means it's opening either left or right. If it was x squared, it would open up or down. So it matches up with what we're talking about. Okay? Any questions on that? Any questions on number 3 as you're looking at that one? Like I said, any algebraic problem that does not have trig in it, solve for t and then substitute and simplify down from there. That'll get you back to the rectangular equation. On the second part, if you remember any problem that does have trig in it, okay, sines, cosines. You had a problem last night on the assignment that had secant and tangent in it. Okay, I'll talk about that in a second. But you are trying to get a trig identity is what you're trying to end up with. Which remember, anytime you're dealing with sines and cosines, cosine squared plus sine squared equals 1. That's what we're trying to get to. Well, in order to get to cosine squared, first I need cosine. So I'm going to take the top equation, and we're going to solve it for cosine of theta. If I get the cosine of theta by itself, subtract the 2 over, and then divide both sides by 4. I end up with x minus 2 over 4. That's what cosine theta equals. Just solving the top equation. If you do the same thing for the bottom equation, if we solve for sine, add the 1 over, divide by 3. Okay, so the sine of theta is y plus 1 over 3. And now here's where I'm going to end up getting rid of the sine and the cosine. Okay? We said, number one trig identity we worked with way back in chapter 5 was cosine squared plus sine squared equals 1. Well, if this is what cosine equals, all I have to do is square it. Remember, when we square a fraction, square the top, square the bottom. So we have x minus 2 squared over 16. And yes, you can leave it just like that. Okay? You can leave it. You don't have to square this out. Matter of fact, I would encourage you not to square it out. Okay? And you'll see why in a second. Plus, so that's cosine squared. And we got to have sine squared. So I square what sine equals, meaning the quantity, y plus 1 squared over 9. And we said sine squared plus cosine squared equals 1. What is this the equation of? That's an ellipse. Both terms are positive, okay, which makes it an ellipse versus a hyperbola. You have the center, if you take a look back, h and k, the center of the ellipse is at 2, -1. It's stretching in the horizontal direction. That's your major axis. A is 4, B is 3. And if you go back up to your graph, that's exactly what we have. There's kind of your center of the ellipse right there. And again, the reason it's only the top half is because we only went from 0 to pi on the parametric. Okay. But it matches up with what we came up with. Okay. Does that make some sense, hopefully? So any type of trig problem, you're trying to get to an identity. Sine squared plus cosine squared equals 1. You always need to solve for sine and cosine. On that problem on the homework, by the way, let me add something in real quickly. What was the problem on the homework? Secant and tangent one. Let's just look at that quickly. What was it? Okay. That part I'm not too worried about. So if you take a look at this one, this is problem 8. Is that what it was? Okay. If you take a look at problem number 8, you can still plug in values of t. I'm going to let you plot the points and graph it. Okay? That you can do. But when it comes to eliminating the parameter on this one, again, what we need is an identity. Do me a favor, let's focus, please. I feel like I'm up here talking to nobody right now. And if you want to know how to do it, then listen. We have an identity. If we take a look on your identity sheet, if you take a look on your identity sheet, we have one that has both secant and tangent in it. It's one of the Pythagorean identities. Well, if we get secant and tangent on the same side, what we have is secant squared, in this case we'll say t, minus tangent squared t equals 1. Okay? If you take that Pythagorean identity and just get the secant and the tangent on the same side, there's your identity right there. Which means, just like we just did on that warm-up, if I want secant squared, I've already got secant by itself. That means what? What is secant squared? X squared. What's tangent squared? Y squared. X squared minus y squared equals 1 is your equation. And if you graph this, because these two, if you really wanted to, you could think of these both as over 1 if you really wanted to. What's the equation of this? Nope. There's one reason why. It's a hyperbola. Why is it a hyperbola and not a circle? because they're not the same sign. If those were both positive, that would be a circle. Because one's positive and one's negative, this is a hyperbola. General rule that I can give you, anytime you deal with secant and tangents, it ends up being a hyperbola. Anytime you deal with sines and cosines, it ends up being an ellipse. Okay? Sines and cosines always give you an ellipse. Secants and tangents always give you a hyperbola. Okay? When you switch things back. So just kind of a quick heads up on this one, more than anything else. I thought about not even giving you this one in the assignment, but I wanted to give it to you because we hadn't talked about it in the lesson at all. So I wanted you to be able to at least see that this was a hyperbola. Okay? All right, here's what I want you to do. Go to the next page of the lesson packet that I gave you. We are going to take a look at applications. And if you notice, those of you who are in physics, these equations should look familiar. Okay, or at least somewhat familiar. Here's your projectile motion that we're going to be talking about, where we're following the path of a projectile. We are going to look at it in its components. Okay, the x in parametrics, the x is representing the horizontal distance over the course of time. The y is representing the height over time. What is the height of the projectile at 1 second, 2 seconds, 5 seconds, whatever it is? So if you take a look, these two equations, these are general equations that you're going to use. Object is launched. V sub 0 is your initial velocity. Okay? S sub 0 in this equation is the initial height. So if you're launching something from the ground, obviously your initial height is 0. If you're launching something that's anywhere above the ground, you have to consider that. Okay? And finally, theta then is the angle at which you are launching it. Okay? What's the angle that something is getting launched to model this? So if you take a look at problem number 7 here, suppose that Jim hits a golf ball with an initial velocity of 150 feet per second at an angle of 30 degrees to the horizontal. We want to first come up with the parametric equations that fit that specific information. Okay? So if we do that, let's plug some things in here. I'm going to come up to the top. So for x, when we're looking at the horizontal distance of that golf ball, we said v sub 0, that's the initial velocity, that's the 150. Let's plug that in. Times the cosine of theta. Theta is the angle at which it's, in this case, leaving his golf club. So cosine of 30. And then we still have times t, and it doesn't matter whether you use a capital T or a lowercase t, it doesn't really matter. But we have t still, our parameter. Okay? Remember, t represents time. So 1 second into this, we can see how far horizontally the ball has traveled. 2 seconds, 3 seconds, 4 seconds, whatever. And then let's simplify this just a little bit, because we've got 150 times, what is the cosine of 30? It's not super nice, but it is square root of 3 over 2. Yep. So let's take cosine of 30 out and put in what it actually equals. It is the square root of 3 over 2, and we still have t there. And now let's just clean it up a little bit. Let's simplify some stuff. I'm going to take the 150 and divide it by 2 right away and leave the square root of 3 there. Which means if I clean that up, we end up with 75 times the square root of 3t. There's your first equation. That's the equation that will model the horizontal distance of the golf ball. Okay. Anybody questions on that? For the most part, just plugging in the information into the equation and then simplifying it down. Okay. The 75 is just coming from the 150 divided by 2. Now, let's do the same thing with y. Take the information, let's plug it in and simplify our equation down a little bit. So in this case, negative 16 t squared plus initial velocity again of 150. What's the sine? This one I'm going to do right away. What's the sine of 30 degrees? 1/2. So times 1/2, and then you still have t there. The reason that's in parentheses, by the way, is that's like your coefficient of t. That's the number in front of the t. Plus, what's s sub 0 on this one? What's our initial height? 0. You're hitting the golf ball, assumed, since they don't tell you that there's any other height, you have to kind of assume that you're hitting the golf ball off the ground. So initial height would be 0, so I really don't even have to put that on the end. I don't have to put a plus 0 down there. And once again, let's clean this up just a little bit. We have negative 16t squared plus half of 150 gives you 75t. There are the parametric equations that fit with this scenario. Okay? Knowing the 150 feet per second, knowing the 30-degree angle, now we can track the path of that golf ball. Okay? That's kind of like, I think I've mentioned this before, that's kind of like if you ever watch NFL football games and they go through and somebody kicks a field goal and they talk about, oh, that would have been good from 57 yards out. This is basically what they're doing. They have technology that's tracking the path of the ball and saying, oh, that would have gone this far. Okay? So it's physics, it's parametrics, it's that idea. Okay? That's basically what they're doing. So if you take a look. All right. Now, let's take this. Notice it says we're going to use a graphing calculator, to simulate the motion of a golf ball. Before we do that, first question I have for you. Let's talk about X and Y. Because we want to try to set up the window here a little bit. If you're thinking about X, horizontal distance, what do you think would be a good minimum value for X? What should we start at? 0. Because that means we're starting that it hasn't traveled anywhere. So we're going to go from 0 to something. What do you think is a good starting point? Anybody that has any idea about golf?
10.
How far do you hit a golf ball?
Say 300 yards.
300 yards? Let's go on the high side.
350.
Okay. Let's go 400. Let's start at 400. Not that anybody's necessarily hitting at 400, but we'll go to 400. How about Y? Height of the golf ball. What do you think we should start at? 0. It's on the ground. And what do you think the maximum height of a golf ball might be? Sure, let's go with 150. Let's try that. These are not necessarily exact, by the way. This is kind of your starting point so we can take a look at some stuff. And then we'll modify from there. All right, let's go to the graphing calculator. All right, let's plug in our values that we just came up with. We came up with our X and Y coordinates, so let's plug those in. You should have when you type this in, by the way, quick heads up, notice right now when I put the square root of 3, if I hit t would be under the square root, and you don't want it under the square root, so just be careful that you arrow off to the side after the square root so that it is not underneath. Okay. So there's our first equation. And the second one we came up with was negative 16t squared plus 75t. Okay. What do I do next? There's always two things you got to do. We got to change the window to fit the situation. Okay? So we have to fit the window. So here's the window right now. Now remember, we got to kind of set everything up. We did that a little bit. Let's start with t. Representing time, what do you think is a good time to start at? 0, right? Okay, so when t equals 0, what do you think we should put for a maximum amount of time? How long do you think this golf ball is going to be in the air? What do you think? 5? 10? Let's go again. Let's go. If you're going to err on the high side a little bit. Let's go to 10. We'll see what happens if we, let's go to starting at 0, going to 10. Remember I told you t step, just leave it at 0.1. What that is representing? That t step. Come on. Can we move the little conversations, please? Focus. The reason the t step is there, again, the reason why it's a nice small number is because what's that saying is the calculator is going to plug in 0.1, 0.2, 0.3, so it's going to plot a lot of points. If that number was bigger, you would not have very many points and the graph wouldn't be very smooth. So that's why you always want that at 0.1 and leave it nice and low. Yeah.
What's the difference between like the t-mins versus like the x-mins?
So t is time. So we're talking about time in the air, and then x is horizontal distance, y is vertical distance, is height basically. So that's, as we work through, next step then, we said x minimum. Well, on the problem, we said let's go 0 to 400. What do you think the scale should go by on x if we're going 0 to 400? 50, 100. There's not a right answer, but if I'm going 0 to 400, I'm probably either going 50, 100, something like that. Let's go with 50. Okay? There's not a right or wrong answer. You can pick whatever you want, but I definitely don't want to go by ones and have 400 little dots on the x-axis. I want to know a little bit less than that. Y values, we said 0 to 150. And what do you think we should go by? Okay, let's do it. All right, let's graph it. Let's see what we came up with. There's the golf ball. Oh, we didn't quite get far enough. This one's a little less. It's not the most realistic problem, by the way. Because remember on the x, we said the x was at 400, which is not super realistic already, and it's saying it's going further than 400 feet. Okay? So let's just modify our window a little bit. Let's go back to our window and we'll modify. Let's go change our x values. Let's go to 700. And we'll regraph and see what happens. See if that's enough.
There it is.
There. So like I said, not super realistic. Approximately, by the way. How far is the golf ball traveling approximately based on your graph? Was it? Somebody said it. Alan, was that you? 600, 650, somewhere in there. If you just count up, that's why, by the way, that's why the scale is important. If you know that each one of these dots is 50, you can figure out approximately where we're at. So it looks like we're right around the 600, somewhere in there. Okay? Did you change your window to what we just did, like all the T-min, T-max, all that?
19149. Whoa! So somebody's hitting me at 7.
That's what this says.
That's,
Let me take a look real quick. Okay. So here's the path of that ball. Okay. You could do this with any projectile. You could do it with a baseball, with a football, with whatever. It doesn't really matter. So let's go back to the lesson here for a second. And now start actually finding different features here that's going on. So we said, I'm just going to sketch the graph. We started at 0, 0. That we know is accurate. Okay. No horizontal distance, no vertical distance. The ball is on the ground. We sketched this, and it ended up somewhere over here. We had said, just based off of the graphing calculator, that was somewhere in the vicinity of 600. Okay? Somewhere in that vicinity. We're going to come back to that. We're going to find it as part of the problem. So first question. When it says, how long is the ball in the air? What are they asking you to find? Time. That means you are going to have to solve one of these equations for t. What do I know if I'm asking how long the golf ball is in the air? What happens at the end? And therefore the height is, which means if I set y equal to 0, okay, if I set my y equation equal to 0, I know at the end it's 0. I can find the time it takes to get to the 0 height. Okay? So now we're kind of going back to quadratics for a second here. We're going to take that equation, that negative 16, we'll do it right here, negative 16t squared plus 75t. And we said we're going to set that equal to 0 because we know At the very end, the height of that ball is 0. We're trying to find the time it takes to get to a height of 0. How do I solve that? You pretty much have two options always. Factor, or if you can't factor, quadratic formula. Okay? Those are your two options. Factor or quadratic formula. This one we can factor. How do I factor this one very quickly? Not a 4. Not 4 is not going to work. But I am going to pull something out. How about a t? We got t in both. Take t out. So if we do that, if we pull t out front, we have negative 16t plus 75 equal to 0. And now we have factored it using the greatest common factor. And now we set each factor equal to 0. First factor is t. So our first answer would be t equals 0. What does that represent? That's the start. Wasn't the ball on the ground when we started? There we go. We just algebraically found that. The other factor will give us the next time the ball was on the ground. Which in this case, if you do that, what do you get approximately? 4.68? Okay? So approximately 4.68 seconds is how long that ball is in the air. Okay? Based on that. So there's your answer right there. 4.68 seconds. Okay? With me so far? Okay. That's the distance. That's the horizontal distance the ball traveled. So now in part D and E kind of go together. When they ask you when is the ball at the maximum height, what are they asking you to find? The vertex. You remember how to find the vertex? If you think back, it's been a while. It's not, well, if you know the ending point, then you can kind of take half, but unfortunately we don't necessarily know the ending point. We know at least half of the time. I'm going to do it a different way though, because the way I'm going to do it is the way it's always going to work. Because in this case, make sure you listen to this because this is the difference between two types of problems. If I know the ball's in the air 4.68 seconds, I could take half of that and that's how long it would, but that only works if this is a full parabola, if the ball starts on the ground. If I was taking that and the ball was up like 10 feet in the air, that's not going to work because we don't have a full parabola then. Okay? So I'm going to show you a different method that confirms that we get half of that. That will always work. If you remember back, if we find vertex, so I'm going to take this equation, our y equation. If you remember to find the vertex, opposite of b over 2a. Remember back to that?
Yeah.
That's how we find, remember the x-coordinate of a vertex. So in this case, this would be negative 75 would be the opposite of b. And if I double a, I get negative 32. And if you take negative 75 divided by negative 32, what do you get? 2.34, which is half of what the time was.
Yeah.
This method will work if that ball is starting off the ground. The half the time only works if the ball is on the ground to start. Okay? So I would recommend this method over the other one just because it always works. So you get 2.34 seconds. That is how long it takes to get to that maximum height. E then, what is the maximum height? What do I do? Yeah, plug it back into your equation and find the actual y value. What's the y value that goes with 2.34 seconds? Okay. Which, what is it? 87 point what? 89? Okay, that sounds right. So you get 87.89 feet in this case. If you take that 2.34 and you just plug it back in to your y equation, that'll give you the vertical height after 2.34 seconds.
Wait, what's the 87.89 then?
That's what I just said.
It's your max height.
If you take the 2.34 seconds, it takes 2.34 seconds to get to that height. All we're doing is plugging the 2.34 in for t and finding what's the height that goes, where are we? What is the height after 2.34?
So 87.
It's the y coordinate. Yeah, that is your height. All right, last question on this one. We said Off of the graph, we knew the horizontal distance was approximately 600. Now we're going to actually find it exactly. Determine the horizontal distance the ball traveled before it hit the ground. Any idea? The math is not hard if you understand what we're trying to do. What did you do? So if we take a look, we have an equation for horizontal distance. It's x. Do I know the time it takes to get all the way through this? It's the 4.68. All you have to do is plug in the 4.68 to find the total horizontal distance. Okay? So if we take 75 times the square root of 3 and we multiply it by the fact that we now know it's going to take us 4.68 seconds for the entire path, you get an answer of 60 what? 607.95. And so
600 was just an estimate.
So our 600 was just an approximate off the graph. There's the actual answer. This golf ball, unrealistically, was hit 608 feet. Okay? Nobody hits a golf ball 600 feet, just so you know. Okay? No one.
What's the world record for the moment?
I don't even know if the longest drive competitions where that's all they're doing if they go 600 feet. Is that what it is? What is it? There you go. The longest drive ever was 515. Oh, yards? Oh, then we're going, yeah, okay, that's different then. That's way different. Then we're okay. This is in feet, so we're 200 yards. So we're good. That's pretty average. Okay. Your assignment for today. I've got a worksheet for you. Again, not a lot of problems. Once you get the worksheet, hang on to it. Don't put it away quite yet because I want to mention two things.
Average drive like 2
All right, two things, like I said. First one, on the first 5 questions, you are just eliminating the parameter. You don't have to plot the points and graph it and all that stuff. Just find the equation, x in terms of y. Number 5 is a little bit of a challenge problem. It's not super long and difficult, but you got to think through number 5. So just a heads up on that one. Number 7 is very similar to what we just did, and so is the problem on the backside. They're both very similar type problems. Okay? Answer key is here for you, at least the final answers of the equations and what you should come up with. Last reminder, this is the final assignment that is due for the 3rd quarter. Okay? And by tomorrow midnight is the deadline for assignments, 3rd quarter assignments. Okay? After that, when I start my grades on Friday, that's it. You're going to do an in-class thing tomorrow. Okay? Something in class that's not another assignment. Okay?